Hello everyone. So in last class we have studied about attacking reagents. We have studied about two types of attacking reagent, electrophiles and nucleophiles. Now we have studied about types of electrophiles and types of nucleophiles. So there are three types of electrophiles we have studied. There is incomplete octet positively charged electrophiles, incomplete octet neutral electrophiles and complete octet electrophiles. We have studied three types of nucleophiles also: negatively charged nucleophiles, neutral nucleophiles and positively charged nucleophiles. So today we will study about electrophilicity and nucleophilicity. So what is electrophilicity? So ability of a reagent to accept electron, that is electrophilicity. Now order of electrophilicity. So in last class I have taught you that incomplete octet positively charged electrophiles, then it will be incomplete octet neutral electrophile, then it will be complete octet electrophile. This will be the order of electrophilicity in the case of electrophiles. Now what is nucleophilicity? See, ability of reagent to donate electron, or better definition will be ability of reagent to attack electrophile. So higher the ability of reagent to attack electrophile, higher will be nucleophilicity. So this is definition of nucleophilicity. Now how can you give the nucleophilicity order? How can you check by the order of nucleophilicity? So I will give some points for the order of nucleophilicity. Like using these points we can decide the order of nucleophilicity. So first point is on moving left to right in periodic table. Always think in terms of electronegativity. Less electronegative, more will be the nucleophilicity. If atomic group is less electronegative, it can easily give us electron. So less electronegativity, more will be the nucleophilicity. Second point, on moving top to bottom in periodic table. Moving top to bottom in periodic table, always think in terms of size. Always think in terms of size. Third, see, negatively charged nucleophile. Negatively charged nucleophile are always more nucleophilicity than neutral nucleophile. Negatively charged nucleophile has always more nucleophilicity than neutral nucleophile. Fourth point is nucleophile having more nucleophilic site. Nucleophile having more nucleophilic site are more nucleophile. Or have high nucleophilicity. So we take one example on this case. See, NH3 and hydrogen, NH2. So in this case we have two nucleophilic sites, this and this one. So in this case this NH2 has more nucleophilicity than NH3. More nucleophilic. So between NH3 and NH2 has more nucleophilicity than NH3, because see, what is the reason behind this? See, whenever like generally reaction takes place in solvent, so whenever solvent is not given, so we take water as a universal solvent. We take water as a solvent because water is a universal solvent. Now in this case, what will happen? Water will interact with NH3 and with nitrogen. It will form hydrogen bond with nitrogen. So here water will interact with this nitrogen, and here also water will interact. But in this case, water is being shared, so it is interacting with this both nitrogen. So in this case, this lone pair will be more available to donate. In this case, this lone pair will be more available to donate. That's why it will be more nucleophilic. Here it is completely surrounded by water. It is more soluble by water in compared to hydrazine. So I hope you understand this. Fifth point. Now nucleophilicity and basicity both have like donating property. Base also donate OH minus and OH minus. So when we will say this, this will act as a here it is acting as a nucleophile or it is acting as a base. How can you decide? By seeing the nucleo, like any compound, we cannot say it is nucleophile or base. So how can you decide? So first is if electron is donated to H plus, then it acts as a base. So if OH minus donating its electron to H plus, then it will act as a base. So here it will act as a base. Second point, if electron is donated to any other atom other than H plus, donated to any other atom other than H plus, then it acts as a nucleophile. Then it acts as a nucleophile. So here suppose this OH minus we have taken, and here we have C plus. Now in this case, oxygen will donate its electron to carbon and will form product. Now 6th point. Now see here, whenever oxygen will try to donate its electron to carbon, so due to this 3 valency of carbon, there will be some steric repulsion. Due to whenever oxygen will try to donate its electron to carbon, these 3 bonds are present, 3 valency of carbons are present. So due to that, a steric repulsion will come. In the case of base, there is no steric repulsion. Only H plus is present and can easily give its electron to H plus. But here a steric repulsion will come. So nucleophilicity also sensitive towards steric repulsion. So you can also here we will write 6 point, that nucleophilicity is sensitive towards steric factor. See, more steric crowding, less will be the nucleophilicity. Because if suppose if this nucleophile has more steric crowding, then like more steric repulsion will take place and will not be able to donate its electron. So nucleophilicity will decrease. So more steric crowding, less will be nucleophilicity. Right here, more steric crowding, less will be nucleophilicity. Now last point, nucleophilicity also affected by solvent. nucleophilicity also affected by different type of solvents. Note down all these points, and now we'll do some questions based on the nucleophilicity order. So write down decreasing order of nucleophilicity. We tell the nucleophilicity order for these compounds. H2O NH3, OH minus, H2O, third, SH minus, H2S, fourth, RO minus, ROH, fifth, NH3, already I discussed this, NH3, NH2, NH2, sixth, phenoxide ion, I am writing the question, you people should just start doing this. Now I will discuss one by one all these questions. So now between H2 and NH3, which will have more nucleophilicity. See, we are moving left to right in periodic table. So oxygen is more electronegative and nitrogen is less electronegative than oxygen. So nitrogen can easily give its electron. So NH3 will have more nucleophilicity than H2O. Here OH minus and H2O. So I have given rule that negatively charged nucleophile will have more nucleophilicity than neutral nucleophile. So OH minus will have more nucleophilicity than H2O. Between SS minus and H2S, SS minus, RO minus, ROH, RO minus. Now NH3 and NH2. So in NH2 more nucleophilistic sites are there, so it will be more nucleophile. Now between O minus, like phenoxide ion and this. Now if you see in this case, this negative charge involved in resonance. Here it is involved in resonance. So it is less available for donation. Here it is available for donation. So in this case, this will have more nucleophilicity than phenoxide ion. If you see in this case, seventh one. So seventh one, if you see on this oxygen more electron density is there because two nucleophilic sites are there. So here negative charge is there. So more electron density. So it will have more nucleophilicity. Then it will come OH minus. Then it will be H2O. Now if you compare between PHO minus, ACO minus, AC means acetyl. Acetyl group is this CH3 C11O. This group is called acetyl group. So in these two, this negative charge is involved in resonance. So it is not completely available for donation. And in PHO minus, this is more involved in resonance. It will have more resonating structure in compared to ACO minus. So this will have less nucleophilicity than ACO minus. And between ACO minus and CH3O minus, CH3O minus will have more nucleophilicity because here negative charge is not delocalized, it is localized. Now between this and this, similar here this negative charge is shared between two oxygen atoms, and here this negative charge is shared between three oxygen atoms. So electron density is decreasing on the oxygen. That's why it will have less nucleophilicity than this one. Now between H2S and PH3, so we are moving left to right in periodic table. So pH has less electronegative than pH is phosphorus. Phosphorus is less electronegative than sulfur. So it can easily give its electron in compared to sulfur. So this will be the nucleophilicity order. Now in this case SiH3, PH2, SH minus and Cl minus. See, we are moving left to right in periodic table, so we have to always think in terms of electronegativity. So electronegativity order is silicon, phosphorus, sulfur and chlorine. So silicon will give its electron easily, then phosphorus, then sulfur and then chlorine. Now what is the order of this one? F minus, Cl minus, Br minus, I minus. See, here nothing is given. I have told you, if nothing is given, we have to take water as a solvent. So water is an universal solvent, and if nothing is given, we have to take water as a solvent. So if you take water as a solvent here, electronucleophilicity order will come 4, 3, 2 and 1. Now I will discuss this, why nucleophilicity order of this all these four groups are this in water. I will take one illustration. See, illustration I will take. Discuss nucleophilicity. Discuss nucleophilicity of flowing salts in various solvents. So we have salt NaF, NaCl, NaBr and NaI. See, generally in the organic reactions, we see the reaction, they will always give like F minus, Cl minus or OH minus or Na plus. they do not give the cationic or anionic part. Why they do not give? We learn here. Generally they give like F minus Cl minus, but you know F minus is very reactive, so they will have cationic or anionic part, but they do not give. Why the reason behind this we learn in this illustration. So we have to discuss the nucleophilicity of flowing salts in various solvents. So first we will take non-polar solvent. In non-polar solvent, what will be the nucleophilicity order for these salts? So what are non-polar solvent? Solvents in which net dipole moment will be equal to 0. So mu equal to 0. So what are the examples of non-polar solvent? That will be in the CCl4, CH2, C6H6, benzene. All these are net dipole moment will be equal to 0. So they act as a non-polar solvent. etc. Now what will happen if you add these salts NaF, NaCl, NaBr, NaI in non-polar solvent? See, these are all ionic, and you know that light dissolve light. So these are ionic and these are non-polar solvents. So this non-polar solvent will not interact with this ionic salt. So salt will not dissociate in this case. First point will be in non-polar solvent this salt will not dissociate. They will remain as it is. They will remain as it is. Salt will remain as it is. They will not dissociate. Because these are non-polar solvent and they will not interact with the ionic compound. Now what is the order of nucleophilicity in this case? So order of nucleophilicity in this case will be I minus, Br minus, Cl minus, F minus. So this is the order of nucleophilicity in non-polar solvent. Why this order? See, now these solvents, like for any compound, for any salt to dissociate, we need the help of solvent. Now this solvent is not helping to dissociate this NaF, NaCl, NaBr and Ni. So if they want to dissociate, they have to break this Ni bond. So in this case, see, bond between sodium and iodine is weaker than bond between sodium and fluorine. So this can easily dissociate. So this will act as a more nucleophilic because this can easily dissociate in compared to sodium and fluorine. So in this case, this is the nucleophilicity order in non-polar solvent. Nucleophilicity order in non-polar solvent. And why this order? Because sodium iodine bond is weaker than sodium chlorine bond, so it can easily dissociate and it can give its electron to the reactant. So this Ni bond is weaker than weakest, so it can easily dissociate into I minus in compared to other compound. So in non-polar solvent which can easily dissociate, which have less bond energy, that will act as a that will have more nucleophilicity in compared to other compounds. Now we'll see in the polar solvent. This is case 1. We are discussing non-polar solvent, nucleophilicity in non-polar solvent. Now we'll see case 2, polar solvent. See, there are two types of polar solvent. polar protic solvent. Polar protic solvent. First we'll see polar protic solvent. Now what is polar protic solvent? First is it's polar. It means in this case mu will be not equal to 0. And protic means proton. Polar protic means protic here means proton. So what does polar protic solvent means? Solvent which can form H bond. Those solvent which can form H bond are called polar protic solvent. Example: H2O, alcohol, carboxylic acid, ammonia. All these can form H bond. So they will act as a polar protic solvent. They are called polar protic solvent. Now what will happen in the polar protic solvent with this salt? Now these are polar and salts are also polar. So they will dissociate the salt. Now dissociation of salt will take place. In this case, salt will dissociate. And now these will be involved in H bonding also. These are polar protic solvent, so they form H bonding. So H bonding formation will take place. Now if salt will dissociate, it will give F minus, Cl minus, Br minus and I minus. Now what is the order of nucleophilicity in this case? Between F minus, Cl minus and Br minus. Suppose you are taking polar protic solvent as a water. So what will happen? So you know F minus is high electron density, highest electron density in compared to other. F minus, then Cl minus, then Br minus, then I minus. This is the electron density. So F minus is high electron density. So H2O can form hydrogen bond with F minus. So H2O will form hydrogen bond. It is high electron density, so it will get surrounded by H2O. H2O will form hydrogen bond with F minus, and it will surround the F minus completely. It will solvate the F minus more. It will also form hydrogen bond with Cl minus. But in compared to F minus, it will form less hydrogen bond. It will also form hydrogen bond with Br minus also. But I minus, because in this case electron density is very less, so it will form very less hydrogen bond with I minus. So I minus, negative charge present on iodine has more availability. It is more available to donate its electron because of less H bonding. See. In this case, solvent is polar protic solvent, and this solvent can form H bond. So, because fluorine has high electron density, it will hydrogen will form H2O will form more H bonding with fluorine, and it will completely solvate the fluorine. Fluorine electron will not available to donate. So, availability of electron is present in I minus. So, in this case also I minus will act as I minus will have more nucleophilicity than other three compounds. So nucleophilicity order in this case will be 4, 3, 2, 1. So here you can write negative charge present. Negative charge present on I will be more available. For donation. In compared to more available for donation due to less electron density in polar protic solvent. You understand what is happening in the polar protic solvent? The F minus, Cl minus and Br minus. Now F minus is high electron density. So it will be attracted more towards the H2O. H2O will be attracted more towards F minus, and it will F minus electron will not be available for donation. Cl minus will be also attracted towards the H2O, but I minus will be least attracted towards H2O because it has least electron density. So its electrons are available for donation. So here also it will act as a more like it will have high nucleophilicity in compared to Br minus, Cl minus, and I minus. So this is the order of nucleophilicity in polar protic solvent. And what are polar protic solvent? Solvent which can form hydrogen bonding. So any solvent which is connected with, if in any solvent hydrogen is connected with more electronegative atom like oxygen, fluorine, and nitrogen. Now that solvent will be called polar protic solvent because they involve in hydrogen bonding. Next is polar aprotic solvent. So in the case of non-polar solvent and polar solvent, polar protic solvent, order is same: I minus, Br minus, Cl minus, F minus, order of nucleophilicity. Now next is case 3, polar aprotic solvent. Polar aprotic solvent. Aprotic means which cannot form H bond. Solvent which cannot form H bond are called polar aprotic solvent. Are called polar aprotic solvent. Now, examples for this will be DMSO is called dimethyl sulfoxide. This is very famous solvent, so if you remember this DMSO, it is called dimethyl sulfoxide. Dimethyl sulfoxide. Next is acetone. This is also a famous polar aprotic solvent. Next is THF. THF. What is THF? Tetrahydrofuran. Tetrahydrofuran. One more is the crown ether. This is called crown ether. etc. These are the some famous polar aprotic solvent which you have to remember: DMSO, dimethyl sulfoxide, acetone, TH, and crown ether. Now, what will happen if we add this salt NaF, NaCl, NaF, NaCl, NaBr, and Ni? Salt will dissociate or not? See, these are also polar solvent, and these are also polar molecules. So salt will dissociate. In this case also salt will dissociate. Now what will happen if after dissociation of salt? Salt will dissociate and it will convert into Na plus F minus, Na plus Cl minus, Na plus Br minus, Na plus I minus. Now if you see this solvent, if you see this DMSO, CH3, C double O, CH3. So delta positive charge is coming on the sulfur and delta negative charge is coming on the oxygen. Now, if you see, this delta positive charge is surrounded by two big groups, and here this delta negative charge is like it's not surrounded by big groups. So this delta positive charge will not, it will not be easy for this delta positive charge to approach the negative charge, to approach the anion due to this large groups. So in the case of polar protein solvent, this delta positive charge will not easily able to approach anion, in this case F minus Cl minus, due to large groups present, due to large groups present, so it will not solvate anion. But delta negative charge in polar protein solvent can easily approach cation, and solvate the cation. Now in this case, because they are not able to solvate the anion, so anion will be present in the free form. Anion will be like F minus, Cl minus, Br minus. So charge on them will be in free form. They are not surrounded by the solvent, because solvent, this delta positive charge present on the solvent is surrounded by big groups. So they are not able to approach the negative charge present on the F minus, Cl minus, Br minus, I minus. So here charge is present on the free form. Charge is present in free form. So in this case, order will be F minus, Cl minus, Br minus, F minus, I minus. So in the case of polar protein solvent, more electron density on the anion, more will be the nucleophilicity. In the case of polar protein solvent, more electron density, less will be nucleophilicity. So just remember, in the case of polar protein solvent, more nucleophilicity, less will be more electron density, less will be nucleophilicity. In the case of polar protein solvent, more will be electron density, more will be nucleophilicity. So second point you can write in polar protein solvent, it will solvent cation but not anion due to steric problem, but not anion. I hope you understand the difference between all the solvent, non-polar solvent, polar solvent. There are two types of polar solvent: polar protic solvent, polar aprotic solvent. Polar protic solvent which can form H bond like H2O, CH3OH, a carboxylic acid, NH3, RNH3. So all solvent in which hydrogen is connected with more electronegative atom like oxygen, fluorine, nitrogen, those are called polar protic solvent. And polar aprotic solvent which cannot form H bond. So these are some famous solvent of polar aprotic solvent which you have to remember, like DMSO, dimethyl sulfoxide, acetone, THF, tetrahydrofuran, crown ether. Now I will give you some questions. We have to tell the nucleophilicity order in different types of solvent. So question will be, compare nucleophilicity in polar, protic and aprotic solvent. In polar, protic and aprotic solvent. First will be OH minus, SH minus, second CH3O minus, CH3S minus, third NH3, PH3, fourth RNH2, RPH2. So you have to tell me the order in protic solvent, polar protic solvent, and polar aprotic solvent. Polar aprotic solvent. So what I have told you, that more electron density, less will be nucleophilicity in case of polar protic solvent, and more electron density, more will be nucleophilicity in case of polar aprotic solvent. So here polar aprotic solvent you can take H2O only, most of the case always H2O will be there. So between OH minus and SH minus, in polar protic solvent nucleophilicity will be 2 greater than 1. In polar aprotic solvent it will be 1 greater than 2. Just opposite of polar protic solvent. In this case also 2 greater than 1. Here CH3O minus, CH3S minus. S minus is less electron density, or it will be less solvated in H2O in compared to O minus. This will be the order 2 greater than 1. Here it will be again 1 greater than 2. In this case NH3 is there and PH3 is there. So nitrogen has more electron density, so it will form more hydrogen bond. So its electron will be not available for donation in the case of polar protic solvent. So here also order will be 2 greater than 1. But in the case of polar aprotic solvent, it will be 1 greater than 2. Similarly, RNH2 and RPH2. P is phosphorus here. So in this case also 2 greater than 1 and 1 greater than 2. So this is the order of nucleophilicity in polar protic solvent and polar aprotic solvent. Now I'll add some two general points. Two notes I will add here. First is, on moving left to right, in periodic table, nucleophilicity and basicity are parallel to each other. It means on moving left to right in periodic table, nucleophilicity and basicity both decreases. On moving left to right, both decreases. Both decreases. So we take one example: CH3 minus, NH2 minus, OH minus, and F minus. So in this case, what is the nucleophilicity order? And what will the basicity order? Both will be same. We are moving left to right in periodic table. So it will be 1, 2, 3, and 4. In this case, both will have both nucleophilicity and basicity. Both will have same order. But in the case when you move top to bottom, on moving top to bottom, periodic table. Top to bottom in periodic table, nucleophilicity and basicity are anti-parallel to each other. Anti-parallel to each other. So on moving top to bottom, like we see in the solvent, if solvent is not given for nucleophilicity, we need solvent. If solvent is not given, we take water as a universal solvent. So in water, on moving top to bottom, nucleophilicity increases, but in the case of basicity decreases. So why is that? So we'll take one example: F minus, Cl minus, Br minus, I minus. So this is by the order of nucleophilicity in this case. Nucleophilicity order will be 4, 3, 2, 1. And what is the basicity order? Basicity order will be 1, 2, 3, and 4. Now why is that? Why the order of basicity is 1, 2, and 3, 4? See, we have said now, when any compound will act as a base, when electron will be donated to H plus. So in this case, because F minus has high electron density, so it will donate its electron to H plus present in H2O. H2 will directly come to fluorine in water. H2 will come to the fluorine, and it has high electron density. So it will donate its electron to H2O more now in compared to Cl minus, Br minus, and I minus. So according to definition, this basicity F minus will donate its electron more to H2O in compared to Cl minus, Br minus, and I minus. So that will be the order: 1 greater than 2, greater than 3, greater than 4. In the case of nucleophilicity, it is not able to donate its electron. F minus is not able to donate its electron because it is surrounded by H2O molecules. Now next example. Now I am discussing one example where you have to tell me what is the nucleophilicity order and what will the basicity order. So CH3O minus, CH3, CH2O minus, CH3, CH, CH3O minus, and this will be tertiary butyl oxide, and CH3, CH3, CH3O minus. Now what is the nucleophilicity order and basicity order? Nucleophilicity order and basicity order. So basicity order we have already discussed in GOC. It will be 4, 3, 2, and 1. Now what is the nucleophilicity order? It will be 1, 2, 3, and 4. Why is that? So suppose if any nucleophile is there, so if here we are taking C plus. Now this carbon has 3 valency, and this 3 valency create a steric repulsion with this nucleophile. If you bring this nucleophile, so if this nucleophile will try to attack on this carbon, so due to this CH3 and due to this 2 valency of carbon, too much steric repulsion will be there. So due to that, it will not able to donate its electron to this carbon. So this will act as a bad nucleophile in compared to CH3O minus. Understand? If base is there, if this will act as a base, so if it will act as a base, it has to only take H plus. There will be no steric repulsion, so it can simply take H plus. So that's why whenever steric repulsion will be there, nucleophilicity will decrease. Now I will give you some question and you have to give the nucleophilicity order. So compare nucleophilicity. First is O minus, O minus. Second, we have to compare the nucleophilicity of these compounds. Third, do these questions. We have to compare the nucleophilicity. Now we discuss one by one. So in question number 8, see here this is cyclic and this is fixed. Now this is not fixed. So if it is not fixed, it will increase the steric repulsion. It will increase the steric factor. So in this case, this will have more nucleophilicity in compared to first one due to a steric factor. If you compare between these two, question number B. Now in this case, this lone pair involving resonance. This is delocalized lone pair, so it is not available for donation, and here it is available for donation. So in this case, between these two, this is the nucleophilicity order, and you know that this is the basicity order also. Now if we compare between these two compounds, so see due to this 4CH3 group, this has more electron density. Then due to this CH3 group, this has more electron density. So more electron density, more will be the nucleophilicity. So this is the order of nucleophilicity in this case. Now if we compare between these two, so these two carbon are sp2 haptides and these two carbon are sp haptides. So this can easily give us pi electron. This pi electron can easily polarize in compared to this pi electron, because these pi electrons are present between more electronegative carbon and these pi electrons are present between less electronegative carbon. So this will be the nucleophilicity order. Now we compare between these three. So now this CH3 has plus S effect and this CH3 has plus I effect. Now due to plus S effect, more electron density will increase on this nitrogen. So more electron density will increase in this compound due to plus S effect of CH3. So this will have highest nucleophilicity, then it will come C, then it will come A. I will compare between A and B here. So this NH2, lone pair present on NH2 is involved in resonance. So it will not be able to donate its electron. And here lone pair is not involved in resonance. So this will have more nucleophilicity. So here B greater than A. This will be the nucleophilicity order. Now if we compare G, so here this will show minus R effect and this will show minus I effect. Now we know that minus R effect dominates over minus I effect. So it will be, in this case, electron density in the ring will decrease in compared to this. It will decrease more in compared to this one. So this one will have more nucleophilicity. Now if we compare between this and this, benzene and chlorobenzene. So chlorobenzene, chloro will apply minus I effect and it will decrease the electron density. So this will be more nucleophile. Now between these three, now this is so plus S effect and just 3 alpha hydrogen. Plus S effect, 3 alpha hydrogen. This will also show plus S effect, 2 alpha hydrogen. Or in this case, we see only 1 alpha hydrogen. Plus H, 1 alpha hydrogen. In this case, only plus I effect will be there. So order of nucleophilicity. This will increase the electron density in the ring. So it will have more nucleophilic. It will be more nucleophilic. So it will be A, B, and C. So this will be the order of nucleophilicity. Now if we compare between these three, so negative charge present on sp3 hybrid carbon, it can easily give its electron. Here it is present on sp2 carbon. Here it is present on sp carbon. So sp carbon is more electronegative. So here negative charge is more stable, most stable. Then it is more stable on sp2. Then it is least stable on sp3. So this is the order of nucleophilicity. Next we will see hard reagent and soft reagent. Hard reagent and soft reagent. Hard reagent and soft reagent. So what are called hard reagent and soft reagent? We will see. So they are divided into two parts: hard and soft nucleophile. Hard and soft nucleophile. And hard and soft electrophile. Hard and soft electrophile. So what is hard and soft nucleophile and what is hard and soft electrophile? It's not like we'll touch the electrophile and nucleophile and we'll see if it is hard, so it will be hard nucleophile. If it is soft, so it will be soft nucleophile. It is not like that. So what is hard and soft nucleophile? Suppose you have OH minus, we have OH minus and I minus. Now in this case, which will be hard nucleophile and which will be soft nucleophile? You know, oxygen has a small size and electron density on the charge density on oxygen is more in compared to charge density on I minus. So this OH minus will be called hard nucleophile and I minus will be called soft nucleophile. So it's about the charge. Higher the charge density, it will be called hard nucleophile or hard electrophile. And if charge is lower the charge density, it will be called soft nucleophile or soft electrophile. So if high charge density is present, higher charge density on reagent, higher charge density, it means hard nucleophile. It means hard nucleophile or hard electrophile. Lower charge density, it can be positive or negative also. Lower charge density, it will be called soft nucleophile and soft electrophile. Now, first we will see the hard nucleophile and soft nucleophile. Hard nucleophile and soft nucleophile. So, hard nucleophile, soft nucleophile. So when nucleophile will be called hard nucleophile. If high charge density is present, so first is high charge density. Then it will be called soft nucleophile when low charge density is present. So when low charge density is present. Third, second. Now when it will call hard nucleophile, when charge will be high, when density of charge will be high, when size of nucleophile is small, so small size nucleophile. Third, here it will be size will be large size nucleophile or soft nucleophile. Now hard nucleophile prefer to react with hard electrophile. Hard nucleophile prefer to react with hard electrophile. So if it is high charge density, it will try to give its electron to those who have very low charge density or like who have very high positive charge density. So it will prefer to react with hard electrophile. And now soft nucleophile will prefer to react with soft nucleophile. Prefer to react with soft nucleophile. Now next point, fourth one. Hard nucleophile prefer charge interaction. Hard nucleophile during reaction prefer charge interaction. Prefer charge interaction. What does charge interaction means? Similarly, soft nucleophile prefer orbital interaction. Prefer orbital interaction. So charge interaction means hard nucleophile have very high electron density. So it will react with the electrophile which is high positive electron density. So it will mainly prefer to react with charge. It will mainly do charge interaction. And soft nucleophile will prefer orbital interaction. So orbital interaction means it will react, suppose like 2p orbital is there. So if 2p orbital is empty, or so it will do orbital interaction, and here it will do charge interaction. It will mainly react with the positively charged electrophile, and it will mainly react with the like BF3, BCl3, incomplete octet electrophiles. Now we see examples of hard nucleophile. It will be H minus, D minus, T minus, F minus, NH2 minus, CH3 minus, CH3, CH2 minus. They are very small in size and they are very high charge density. So these are all act as a hard nucleophile. Soft nucleophile will be I minus, Br minus, Cl minus, etc. So they will act as a soft nucleophile because they have very large size and their electron density is less. Now we'll see hard and soft electrophile. So all things will be same in the case of hard and soft electrophile. Just a point of hard and soft nucleophile. Hard and soft electrophile. So we'll see hard electrophile. Here it will be high electron charge density. Hard nucleophile will be high electron charge density. And here it will be low electron charge density. Low electron charge density. Here we will see hard electrophile. And soft electrophile. So in the case of hard nucleophile, high charge electron density is there, and here it will be high positively charged electron density. High positively charged density will be there, and here it will be low positive charge density. In the case of soft electrophile. Second point, it will be also small in size. If size is small, so more positive charge density will be there. Here, large in size. Now third point, see, just like hard nucleophile prefer hard electrophile, so hard electrophile prefer hard nucleophile. Hard electrophile prefer to react with hard nucleophile. And this will prefer to react with soft electrophile will prefer to react with soft nucleophile. In this side. We'll have fourth point. Just like hard nucleophiles prefer during reaction charge interaction, similarly hard electrophile also prefer charge interaction. So hard electrophile during reaction prefer charge interaction. And soft electrophile prefer orbital interaction. So I will give some examples of hard nucleophile, hard electrophile. In this case, it will be H plus, D plus, T plus, NO plus, NO2 plus, CH3 plus, etc. These are all hard nucleophile. An example of soft nucleophile will be I plus, Br plus, etc. So these are hard nucleophile and soft nucleophile. These are terms which like sometimes they ask in the exam, but not that much important. Now I will give you some question and you have to identify electrophile and nucleophile in these questions. So identify the question is identify electrophile and nucleophile involved. Identify electrophile and nucleophile involved. Between these two, which will act as electrophile and which will act as a nucleophile, you have to tell. Now we can identify which one will be electrophile and nucleophile in this reaction. So in this case, see, this is simple. Here it is OH minus and here on carbon positive, delta positive charge is there due to chlorine. So this will act as a nucleophile and this will act as a electrophile. This is nucleophile in this reaction and this is electrophile. Now in this reaction, now I have told you that Br2Cl2 and R2 in all the organic reaction, in whole organic reaction that we have is a electrophile. So Br2 here it is electrophile and CH2 ethene is nucleophile. In this case O minus is there and CO2. CO2 is a complete octet electrophile. This is also electrophile and this is nucleophile. Now this is delta positive charge on carbon and RO minus. Simply this is nucleophile and this is electrophile. In this case, this is nucleophile and this is electrophile. Delta positive charge on carbon, so it will act as a electrophile. Now see here. Here it was acting as a electrophile and here it was acting as a nucleophile. So some elements can act as both. It depends. Here it has more electron density and it will give its electron to H+. So in this case, it will act as a nucleophile and here it is acting as a electrophile. So some compounds can act as a both electrophile and nucleophile, depends on the reactant. Now here ROH is there and PCl5 is there. Now you know phosphorus has vacant d orbital. Phosphorus has vacant d orbital. So it is vacant d orbital. So if any element has vacant d orbital, we have said that FeCl3, SbCl5. So it will act as a electrophile and ROH will act as a nucleophile. In this case, on this carbon delta positive charge is there due to this chlorine and this Na plus RO minus. This is RO minus, this will act as a nucleophile and this will act as a electrophile. Now if you see this compound SOCl, sulfur has d orbital, so it will act as a electrophile and this will act as a nucleophile. Now you know benzene and Br2. So you know benzene act as a nucleophile and Br2 will act as a electrophile. PCl5 empty vacant d orbital, so it will act as a electrophile and this ether will act as a it will act as a nucleophile because of lone pair. Now IBr act as a electrophile and this will act as a nucleophile. Similarly here delta positive charge is there, so it will act as a electrophile and this is BH4 minus. This will give Na plus and BH4 minus. So this will act as a nucleophile. So that's it for today. Electrophile and nucleophile completed. Next class we'll see. Thank you.